Hello, in today's video, we are going to be calculating the equilibrium constant from given concentrations. So in our first example, we have acetic acid, and the equation shows us its ionization. It ionizes to make the hydrogen ion and the acetate ion, and then they give us the concentrations at equilibrium. So it's important that we know that these are at equilibrium. Therefore, we will be able to plug these concentrations directly into the K expression. So first thing we are going to start with is writing out the K expression. So K is products over reactants. So it would be the concentration of the hydrogen ion times the concentration of the acetate ion all over the concentration of the acetic acid. Okay, then from the problem, we can plug those values in. So the hydrogen concentration is 5.44 times 10 to the negative fourth. The acetate ion is the same, so we could have just done squared if we wanted to, because either way it's going to be the same thing, divided by the concentration of the acetic acid, and that is 1.65 times 10 to the negative second. All right, so we put that all into our calculator, and that gives us a value of 1.79 times 10 to the negative fifth. So again, all we did was write the K expression for the reaction, plug in the concentrations that they gave us. The reason why we could directly plug the concentrations in is they told us those were the concentrations at equilibrium. And then we got a value that is less than 1. So that tells us that the reactants are favored. We also know that by looking at the concentration of the reactants. That's our bigger one, so we know that the reactants are favored. All right, now in our next example, we are going to be set up a little bit differently. We are going to know some of the initial concentrations and not the equilibrium concentrations. So it's very important to note that only the equilibrium concentrations can get plugged into the K expression, because the K expression is the equilibrium expression. So only equilibrium concentrations can get plugged in. So if we only have initials, we can make an ice chart. So what we do there is if we had a reaction like A plus B is at equilibrium with, say, AB. Okay, so if I started with 1 molar solutions of A and B and no AB, that would be my initial concentrations. My C, the change, would be based upon stoichiometry. So I'd be losing a certain amount of B. If these are all coefficients of 1, then it would be just minus 1x, and I would be gaining AB. Now, your equilibrium amount would then be 1 minus x, 1 minus x, and x. Normally, they would give you one of those, and you could find the value of x, and then you would know the equilibrium concentrations, and then you could plug into K. Now, let's just say there was a 2 here. Then it would be plus 2x, and so on, because the change would be dependent upon stoichiometry. All right, so we're going to take a look at this example. We have H2 plus I2 makes 2HI. And they tell us that initially the hydrogen concentration is 1 times 10 to the negative third, and the iodine is 2 times 10 to the negative third. Now notice, even though these are in a 1-to-1 ratio, they do not need to start with equal amounts, because you can open up the container and put any amount in there. So as long as there is some of each of the reactants, that is all that you need. So they do not need to start with equal amounts, even if they are equal stoichiometry to each other. All right, we're not starting with any HI, so that starts out as 0. My change would be minus x, because they're in a 1-to-1 ratio, plus 2x. So it's 2x because of the coefficient of 2. I know that I would be losing my reactants, so that's why the reactants are minus x, and I know I am gaining the product. So that's why that is positive. Now, if 1.87 is the equilibrium concentration, 1.87, sorry, times 10 to the negative third is the equilibrium concentration of the HI, I can use that to solve for x. So therefore, x would have a value of, x's value would be 9.35 times 10 to the negative fourth, and that would be molarity if we were, working with our units, because these were all molarity to start with. So therefore, my equilibrium concentration of H2 would be 1 times 10 to the negative third minus this value that I had just calculated, minus x. And I would do the same thing to get the concentration of I2 at equilibrium. That was 2 times 10 to the negative third, again, minus x. So I would plug both of those into my calculator. All right, so once I do the subtraction in my calculator, I get the equilibrium concentration of H2 to be 6.5 times 10 to the negative fifth, and I2 to be 1.065 times 10 to the negative third. Now, normally, I would be writing this on my paper a little bit larger, and then I would have been able to do this work here in this box there. Now, once I have my 3 equilibrium concentrations, now I can just plug them into my equilibrium expression and solve for K. All right, so all I did here was recopy over the information that we figured out on the previous slide. So now we are at the step of solving for K. So first thing we do is we write our equilibrium expression. So that's going to be HI squared over the concentration of the H2 and the I2. Then we will plug our values in. So 1.87 times 10 to the negative third squared over 6.5 times 10 to the negative fifth times the 1.065 times 10 to the negative third. Again, this is a equilibrium expression. Therefore, only equilibrium concentrations can go into the equilibrium expression. So you cannot put the initial concentrations into the equilibrium expression. All right, once we plug everything into our calculator and do our math, we get a value of 51. So again, you took your initial concentrations. The change is based upon the stoichiometry. From the known value of HI at equilibrium, we could figure out X, and then we could figure out the concentration of each of our 2 reactants. Then we could plug everything into the K expression and get our answer. We will be doing this a lot, so you will get a lot of practice with this skill.